So, any questions? I have posted your ninth quiz, which will be due Tuesday at 5 o'clock. I think I'm probably gonna grade that quiz myself because I hopefully will be quick enough to get it back to you Tuesday night before you get it. So as soon as you submit your quiz, I'm gonna try to get it graded so you'll have that part of the feedback too. Don't forget we have a review session Monday. I'm gonna double check on that because I have not heard back from people yet, but it will be. Okay, questions? All right, so what I wanted to do is I kind of want to pick up where I left off. We're gonna do 2A, leaving we're at 2-9. Also Monday, I'll have an unstructured review in class as well. So Monday, bring your questions, kind of, and we'll handle some of them then. Okay, for this problem, I want to find the basis for the column space of A, and I'll have to tell you what A is. And I'm going to reuse this example a little bit later in the lecture as well. A is going to be matrix 1, 1, 4, 2, 1, 5, 6, 3, 5, 11, 7. -2. So I want to find basics of the column space of this, and if this was so we're going to do the column space of this here. Now we go about this the same sort of fashion that we go about finding basis for the null space, right? We do row reduction and see what comes out of it. So let's do the row reduction. I want to first use this, wipe out these below it. So multiply by -2 and add here. So that's going to be 0, -1, -1. -2. Multiply by -3 and add here. 0, 2, 2. 3, so that's going to be -1. And multiply by 2 and add here, and I get 0, 6, 6. 2. So that's going to be okay. So the next thing I'm going to do is I guess I'll take this -1 and wipe everything else down below it. So multiply by 2 and add. And this is going to be -5. And I'm going to do the same thing here, except I get multiply by 6 to take this out. So that's going to be 1. Okay, so far. Now, at this point, let me ask you this. Can anybody identify where the pivot columns are? Like, I haven't completely wrote this yet. Yeah.
Column 1, 2, 1.
Okay. pivot column here, agree? Pivot column here. Not a pivot column, and there'll be a pivot column here. In fact, I can take the slides and just nuke everything above it if I want it. Now, actually, I am going to take this one more step for another echelon form. Another thing that I could do, I'm going to take this one, move all this stuff here. So I can take 1, 1, 3, 0, 0, minus 1, minus 1, 0, 0, 0, 0, 1, 0, 0, 0. Everybody okay with it? What I did is I used this one here to just kind of take these out. And then I moved the 0, 0, 0, 1 here and put the also. So again, the pivot columns don't change as they should not. It's 1, 4. Right? Now, here's the delicate thing about finding a basis for the column space. The pivot columns are 1, 2, and 4, right? But you can't use those columns on a reduced matrix. You have to go back to the original. So to answer this question, a basis for column A are these three things. First column, 1, 2, 3 minus 10. Second column, 1, 1, 5, 4. And the third column, 4, 6, 11. Can somebody give me there's a quick way, look at these columns here that were in the reduced matrix. I can see very quickly that those three columns can't possibly be a basis for the column space. These three can't possibly be. Can anybody tell me a quick way that you can look at that? Let's see. In the column space, how big are these vectors? What size are they? There are 4 rows by 1 column, right? So they're 4 tall. Do any of the vectors in the column space have non-zero entries in the 4th position? These certainly do, right? I've got a 5, I've got a 4, I've got a -2. Everybody agree? Is it possible to use these 3 vectors to make something that has a non-zero entry in the 5th position? No. So there's no way that these can be a basis because they don't give you everything, right? That's kind of a gut check that we have to use the ones from the original. Okay. Yes.
So in definition for like all A, all B, it says the subspace of all A is spanned by the column A.
Correct.
So you can't span the original because there's zeros in the fourth one.
Right. These cannot possibly span the column space. And the reason why, would you agree that this vector 1, 2, 3, -2 is in the column space, right? It has to be because it's one of the columns. Everybody okay with that? So how can you take a linear combination of this and get something with -2 in the 4th quarter? It's impossible because you've got zeros across the board. That's why you have to use the original ones out of the dimensions. By the way, what does this tell us about this column right here? I don't have to use the basis, so that must mean that there is a linear combination of these 3 that make this column. You guys see what it is? Yeah.
The 4th column. I mean, no. I was just.
Well, there's some way to do it, and I didn't want you to go too fast on me. I'm going to come to that in a minute. I'm going to express this later. But let me leave this up here now. So this is my original matrix A, and we now know that the column space is spanned by columns 1, 2, and 4. Right. Okay. let me give you, before we might revisit this, let me give you the fact here. We're going to talk about mention and rank here. I want to give you some theorems. And one of the theorems I'm going to give you is called the rank-nullity theorem. And I'm not going to show that this is true yet. I'm just going to give it to you to use, but we will see later why this is true. So here's one more. Mention right here. So let me start with this fact. Suppose you have the subspace. Okay, so suppose we have a subspace Rn, and suppose V1, V2, Vk is a basis. Somebody quickly remind me, what does it mean to be a basis?
Yeah, the set of vectors spans that space.
Okay, that's one thing. You need something else.
They're linearly independent.
They're linearly independent. That is correct. So what it means for this set to be a basis is it means all the crap in here is a linear combination of this. And this set is linearly independent. Right? Y'all remember that? So that's an important concept. So X. Unique. So what the linear independence gives you is everything in the subspace can be written as a linear combination of vectors, but linear independence ups the voltage. This representation is unique, and I'll show you how this works. Let X be in the subset, any vector you want. What do we know? And I'll put a little pad on this. X is A1 B1 plus A2 B2 plus A. That's what it means for X to be in the span. There is some combination A1 B1 plus A2 B2 that adds up to X, where the A's are just numbers. Right? Okay, well, now let's just suppose, for giggles, that there's another way to do this, right? So suppose we can write X a different way. So suppose X is B1 B1 plus B2 B2 plus BK BK. Suppose we could write it another way, just second word. Now, let me subtract this. What happens when I take X minus X? I get the zero back. Good. What happens when I subtract this? Well, let me kind of abbreviate. This is A1 minus B1, B1, A2 minus B2, B2, AK minus BK, BK. Right? Okay with that? But these vectors are linearly independent, right? So what does that mean? So here's a linear combination of these V's that add up to the zero vector, right? What does that mean about all these coefficients? Yeah, they're all zero. because the vectors B1 up to BK are linearly independent. So A1 minus B1 is 0, A2 minus B2 is 0, all the way down to AK minus BK is 0. And even though my parents are cousins, I know that this means that A1 equals B1, A2 is B2, and AK is BK. Correct? And so, how about them apples? There's only one way to do this. Okay. So, that is one of the reasons why linear independent representation is so important. Because there's only one way to do this. Okay. Any questions? So, definition. Let me. I'm going to use this notation a lot. It's just sometimes I'll need a basis here. This is just a collection of vectors here. Let's say if X is in S, so if X is in the subspace X generated by B, let's see where S is span the set of vectors. Then X is equal to C1, D1, plus C2, D2, CK. And the choices. The choices you see out are unique. That's what we showed over there. We write vector X B. And what I mean by this is as equal to C1, C2. These are the coordinates of vectors. So, yeah, so let me give you a good example of this. So I'm going to give you a couple of examples. Example. Let's look first in ours. I claim this vector one minus, or one, and one minus one is the basis for it. By the way, I'll show you what the vector look like. One of them looks like this, one of them looks like this. And I claim that anything in R2 is a linear combination of these two. See if you can show that these are linearly independent. All you have to do is put them in a matrix and show that it's got two different columns, and that's not too much of an issue. Let me give you an example, and then I'll give you, let me give you a numerical example, and then I'll give you more generality. Right. Vector. 2, 0. And B coordinates. Anybody see how to do this? How to write the vector 2, 0 as a linear combination of these? Yeah. Right, all you gotta do is 1 times this plus 1 times this. Right, agree? That one's fairly obvious. So using this notation here, the vector 2, 0 and B coordinates is 1, 1. And another way to translate that is 2, 0 in standard coordinates is 2 times E1 plus 0 times E2. Right. And that can be rewritten as 1 times 1, 1 plus 1 times 1 minus. So the standard basis coordinates would be this, and if I translate this 2, 0 and B coordinates, this means 1 times the first vector and 1 times the second. In fact, I'll do this more generally, and this will show actually the spans. Let's write anything. So how would we do? Well, I'm gonna do a little computation. And again, it just blows my mind how many times this comes up over and over again in this course. Is really what we're doing is we're trying to write this as let's say x1 that's essentially what we're doing, and our new coordinates should be new. Everybody okay? That's what we're doing. We're trying to figure out how to write AB this way. Well, again, this is a system of equations. So let's just make an augmented matrix here. And see where we go with this. I guess the most intelligent thing I can do, make my work as short as possible, is take -1 times the first row and add it to this. -1, so it's -2. This should be -8. Okay. And I'm gonna take this on the Rover reduced echelon form so I can just read things out. 0, 1, A minus B over 2. And this is 1, 1A. Right. All I did is I divided the bottom row by -2. And this is, so I guess I got to multiply this by -1 and add it here. And so I've -1 and add it here. And this would be A minus this, so it's going to be, let's see, so that's two A over two minus this, so it would be A plus B. So my new coordinate should be this. They should be B coordinates, should be A plus B of two. And we can check this, right? Because if you look at A plus B over two comes back to 1 plus A minus B over two comes back to 1 minus. Well, this gives me my top entry should be A plus B over two. We'll say minus B over two. B's cancel, so I get 2A over two, which is A. And in the other one, I get A plus B over two minus A minus B over two. So that's going to be two B's and no A's. So and so I've come full circle and verify this. Everybody okay? We're going to do some stuff with changing coordinates. I think it's important for us to see this right now. Let me do another example. Let me go back to column 1, 2, and 4 are bases for column A. This is the example we looked at before. Let me repeat it for you. Some columns that were basis are this 1, 2, 3, minus 2, 1, 1, 5, 4, 3, 5, 11, 0, and 4, 6, 11, 5. So columns 1, 2, and 4 form a basis for the column space. Let's kind of go through this here. Let's call this B1, B2, and B3. Now, the first thing I want to do is, let me point out that the third column, since the first, second, and fourth columns are a basis, that means they should span the entire column space. The third column is in the column space. So it should be a linear combination of columns 1, 2, and 4. Let's check that. Let's check it. So let's do an augmented matrix. 1, 2, 3, -2, 1, 1, 5, 4, and 4, 6, 11, 5. By the way, before I finish the augmented matrix, you could use this matrix right here to show that those three vectors are in fact linearly independent, which is one of the things you need for a basis. And the way you would do it is just row reduce it and make sure that you've got that all three columns are pivot columns. And that's easy to check. But I'm gonna actually use this augmented matrix. I just got to find out if the system's consistent. I've got to be able to write this third column here in terms of these other three, and then I'm going to write it in coordinates. Really, all I'm going for here is the system needs to be consistent. So let's see what happens. I'm going to use this to eliminate the stuff I've written. 1, 1, 4, 3. So I'm going to multiply this by -2 and add, -2 and add, -2 and add, -2.5. That times -3 and take this out, 0. That's going to be a 2. -3 and add is -1. Yes. -3 and add is 2. And then I'm going to multiply by +2, take this out. Make 0.6. That's going to be 85 is 13. And what I'm going to multiply by 2, so it's going to be 6. And I'm hoping that this is consistent here. So I guess my next step is I'm going to use -1 to take this out. 1, 20, 40, 20. I'm going to use the -1 to take out the stuff below it, multiply by 2 and add, well, -1, -2, 1. Multiply by 2 and add, so it's going to be 0. That's going to be -5. That's going to be 0. And multiply by 6 and add. That's going to be 1. And that's going to be 0. How about the numbers? Notice these last two equations. Basically, what this means is actually let me kind of reduce it here. Maybe a couple more steps. More like 0, 0, 0, 1. 0. So multiply this by 5 and add, I get the row of zeros. Multiply this by 2 and add. Actually, you take 0 minus 1, 0 minus 1. And take this out. That's going to be 1, 1, 0, 3. And zero, 0, 0, 1, 0. I am going to add this to this, and I'm going to get 1, 0, 0, 2. And I'm going to change the sign of this. This system is consistent, right? Row of zeros, no problem. And this actually gives me x1 is equal to 2, x2 is equal to 1, and x3 is equal to 0. Okay. So the system is consistent. I've got the solution, and actually, the third column, which was the vector 3, 5, 11, 0, in B coordinates would be as, in this case, B1, B2, B3. So it's just these three columns, first, second, and last column, is two, 1, after our solution. And again, I'll verify that. Because what this literally means is this is 2 times B1, which is the first column, plus 1 times B2, which is the second column, plus 0 times B3, which is the last column. 4, 6, 5. And if you just check this out, then what this is 2 and 1 is 3. This is 4 and 1 is 5. This is 6 and 5 is 11. And this is -4 plus 4 is 0. And there you go. Like, see that? Okay. And again, since this is a basis, it's a linearly independent set, this is the only way to write this in deep coordinates. Okay. Questions? Okay. By the way, I have used the word dimension in this class, appealing to your intuition in linear algebra, but now I'm going to be more careful with it. When you think of one-dimensional, what do you think of? A line, right? Two-dimensional, what do you think of? A plane, right? Because in a certain sense, the one-dimensional on the line, so I'm going to talk sort of like a physicist here, it's like a car on the road. You only have to, you can only move in one direction, right? And if I give you one parameter, I know exactly what you are, right? A plane is like a ship on the ocean, right? Because now you need 2 coordinates to specify where the boat is at any point in time, right? 3-dimensional space, that's even more complicated, right? Because just because I tell you, where the floor plan is, like what the coordinate is right here, you can go up and down forever, right? A basis is sort of like that. It's the number of vectors that you need to span the space, a minimal number of vectors that you need to span the space, and they're sort of what determine where you're at in space. So let me make this precise. Definition. But S and R can be space. And actually, it doesn't really have to be a subspace of Rn. This can be done much more generally. The dimension of S is the number of elements now. I'm playing a little bit, so the mathematician in me, I have to sort of give you a caveat. I'm playing a little bit fast and loose. That definition assumes a couple of things. Number one, it assumes that a vector space has a basis. And that is absolutely true. You can take that as fact. Any vector space has a basis, right? And number two, actually, it's not too difficult to show that a basis, that any Rn has a basis. That's easy. But actually, even infinite dimensional vector spaces have bases, and that requires more. And number two, I'm assuming something else. I'm assuming, sort of in this definition, that if I have any 2 bases of the same vector space, and believe me, for most vector spaces, there's infinitely many bases. Any 2 different bases have the same number of elements. This is also true in the playground we're in, right? If I have 2 bases of a 10-dimensional vector space, they will both have 10 elements. That is always true. What's the importance of a basis? Well, how many points are there, for example, in the plane? There's a lot of them. Everybody agree? There's infinitely many vectors in a plane. But a plane is a 2-dimensional vector space. And what makes it really economical is the following. Take any of those infinitely many vectors, points in the plane, you only need 2 of them and their parameters to specify where you are. So it takes dealing with something big like a plane or a space, and dealing with just a finite set of things and some parameters. Let me give you another, hopefully give you Example. R2 is two-dimensional. And there are many, many different bases to this. E1, E2. This is standard basis 1001. 1, 1, 1 minus 1. Give me two numbers.
5 and 7.
You can give two other numbers. How about that? You got built another basis for me. There's lots of bases for R2. By the way, anybody tell how I know those two are linearly independent?
You can't. I don't think it's good.
Right, there's no linear combination of these, the non-zero linear combination equals zero, because basically they're not on the same line. It's actually fairly easy to do two-dimensional checks on that. In general, Rn is n-dimensional. And one basis, I'll just write one, is E1, E2, up to En. And this is just one and a stack of zeros, 0, 1, zeros, all zeros, and then a 1 at the end. That's the standard basis for Rn. Another definition. Definition. Let A be your favorite n by n matrix. When I say the rank of A, so here's my definition. The rank of A is the dimension of the column space of A. Oh, and let me also point out that the dimension of the zero vector space would take to be C. Right, so if your vector space is only the zero vector, and that's dimension 0. So what's the rank of A? Look at the column space and figure out what its dimension is, because after all, it's a subspace of Rn. If you look at that column space, and take its dimension, that's what we call the rank of the matrix. And let me throw this in. This is sort of more than a definition, because I'm giving you some factoids here. This is actually also equal to the number of linearly independent columns of A, and it's also equal to the number of pivot columns. Right, so that's an easy way to tell. If you want to know the rank of the matrix A, just row reduce it and count the pivot columns, and that's the rank. Right, so from that perspective, not too bad, right? Okay. So let me give you got 3 more theorems for you. This theorem is called rank nullity theorem. And it is a very powerful theorem, and I'm going to give it to you now, right? And we're going to see why this is true later, but we're not quite at the place where I can get that machine to be out. So it's sort of like giving it to a 5-year-old, but I'm going to do it anyway. If A so suppose you have your favorite n by n matrix, then n, which is the number of columns in this matrix, is equal to rank A plus dimension of the null space. Like I said, we're going to see this later. But this is amazing, right? Because, for example, suppose you have a matrix with 20 columns, right? And suppose that you suppose you figure out the dimension of the null space, right? Which is basically the number of free variables you get when you row reduce it. Then let's say that the dimension of the null space is 9, right? You have 20 columns, this is 9, and the rank must be 11, right? This is absolutely amazing that the rank, that is the number of, the dimension of the column space is, if you add that to the dimension of null space, it adds up to exactly the number of columns. And this is called basis theorem. If S and Rn is a subspace, and dimension of S is equal to K, which of course is necessarily less than or equal to N, then any linearly independent set subset of S with K elements spans S. Spans S. So if you have a subspace of dimension K and you have exactly K linearly independent elements, then that set is a basis for K. Also, any set of K elements that spans S is a basis. So this is sort of the other side. This is sort of the other edge of the sword, if you will. If you have K linearly independent elements, and you know the dimension's K, then that's a basis. And on the other hand, if you have exactly K elements that span, that set has to be linearly independent. Any questions? I am going to end with one theorem that kind of tacks on. So this is sort of adding on to this theorem about invertible matrices. Given what we learned today, let A be, in this case, a square matrix. The following are equivalent. So again, this means that either all these statements are false, or all these statements are true. The columns of A form a basis for Rn. So suppose all the columns form a basis. 2, A is invertible. 3, the dimension of the column space of A is precisely N. 4, the rank of A is N. 5, the null space of A is precisely the zero vector and nothing else. And the dimension of the null space of A is zero. This all follows from, basically, this all follows from definitions we've done today. So this just kind of adds more about convertibility. Any questions on that? Any questions? Okay, folks, don't forget you got a quiz due, at 5 o'clock today. The next one we do Tuesday. I'm gonna see what's up with the review session, but it will be going on Monday. And other than that, you guys have a good weekend and we'll